Okay, so the plan for today is just to continue with our discussion of normal distributions in chapter 6. Note that the midterm exam grades were updated. I finished going through and looking over those for partial credit this morning. So check back on my stat lab at your at your updated midterm exam grades. Um, Probably I would say half to three quarters of students got some partial credit or full credit for some different problems. So you can look through the problems um, that were marked wrong, and you can see where the additional credit was added. If you have any questions, just send me an email, pop into office hours, and I'm happy to answer any questions you have about the partial credit or anything like that. Um, it did generally seem like the class did well in the exam, and the scores were pretty reasonable. So I don't remember the averages and so on right off the top of my head, but it did seem like a good showing on the exam. And then the quote of the day today is from I suppose a scientist, maybe you might call him statistician. I'm not 100% sure. From about 100 years ago, Veblen, and the quote goes, "The outcome of any serious research can only be to make two questions grow where only one grew before." And I think this is closely related to the Epictetus quote about conceit of knowledge getting in the way of learning. That if we're doing research, we, might think of research, we might think of, journal articles or these kinds of highbrow research uh, results as answering a ton of questions, and now we know more about the world. But I think, sometimes that's the wrong way to look at things. Sometimes the right way to look at things, especially from a kind of an inquisitive standpoint, is to say, okay, well, often in the process of answering one question, we come up with two more questions. We don't want to answer a question and then think we know everything about a certain topic. When we answer a question, we want to think, okay, how much more do I know about this topic? And usually what happens is we know a little more, but knowing a little more gives us more insight and allows us to ask even more questions on top of that. So I think that's just an interesting perspective for learning and for progress in really any scientific field. Okay, so I want to quickly, because it's been about a week and a half since we last met, I want to quickly just review the standard normal distribution. And then we'll continue on to the general normal distribution. I'm sorry, my allergies have been going haywire with kind of spring coming around and with it being, generally rainy and a little cruddy outside. Also, my Adobe decided to update itself at some point, and uh, I haven't figured out how to get the settings back to the way that I liked them before. So there we go. I've got it set up. Let me switch my share here. Sorry, it's taking me a little longer than usual to get my tabs coordinated. My OneNote is crashing at the moment. So let me just restart my OneNote. I think that should fix the problem. I love technology when it works, but when it doesn't, it's makes me want to pull out my hair, and I don't have a lot of it left to pull out. So okay, there we go. I think we are all set up now. Okay, so recall from before break, we talked about the standard normal distribution. We had the normal distribution, symmetric, peaked in the middle, tails off to both sides. And the standard normal distribution has a mean of 0. And these inflection points are one standard deviation away from the mean. And for the standard normal distribution, the standard deviation is 1. Now, general normal distributions, we can have a different mean. We can have a different standard deviation. We can have the mean being any real number and the standard deviation being any positive real number. But this standard normal distribution is special because we're going to see that we're going to kind of reframe more general questions in terms of the standard normal distribution. And then we can use a table like this one with one front and one backside to answer questions about any normal distribution, right? We don't want to have a book full of normal distribution tables, one for each combination of mean and standard deviation or something like that. So this way we can get away with just having one table for the standard normal distribution, and we can reframe other questions about other normal distributions in terms of this one. But let's warm up by just asking some questions directly about the standard normal distribution. So if I wanted to know what's the probability that z is less than 0.347, on my picture, I see 0.347 is a bit to the right of 0, so it's a bit to the right of the peak here. And then remember, in continuous distributions, probabilities are represented by areas. So I'm looking for the area to the left of 0.347. I'm looking for an area to the left, and that's directly what my table gives me. And I'm looking for the area to the left of a positive number, so I'm looking on the positive z-score side. And remember, my index, column, and row are related to this z-index here, this point on the horizontal axis. And the field of the table, the middle numbers here, these correspond to areas or probabilities. So I'm looking for the area to the left of 0.347. I see that my table is only accurate to 2 decimal places, to the 100th place. So I'll approximate this with probability z less than 0.35. So that's 0.3 getting the 10th place right. I'm just not having a good tech day today. All of my tech is being a little wonky. So there's my 0.3 row, and then my 0.05 column to get the 100th place right. And it looks like they intersect at 0.6368. Or 63.68%. Does that mesh with what I see in my area? Well, I noticed that my area includes all of the area to the left of 0 plus a little extra. So this should be bigger than 50%. But it shouldn't be like 95%, right? If we drew this at all reasonably accurately, we have a decent chunk of the right-hand tail that's missing. So yeah, 63 or so percent, that seems pretty reasonable. Let me try to restart my Adobe now and see if that fixes the... Oh, great. Now Adobe's installing another update. Let's see if it will. I thought I had everything ready to go, and apparently everything is crashing this morning. I think they just want to install updates so they can try to sell you more stuff. All right, well, I'm hoping that I might have to just open this in Chrome. Can I do that? All right. Can say thank you to Google for for being not nearly as glitchy as so many of the other programs out there. So I'll just run it in Chrome. There we go. All right, so if we have a question like this, probability Z bigger than 1.735, this one's a little different. We see that our table gives us areas to the left. So I can't just look up an index of 1.74 or so on my table. So how do I get this area? Here's, say, 1.735. I'm looking for the area to the right. How do I get this into a question about an area to the left? That's 3, 5 down there. Well, I noticed that I can construct this area by taking the whole area under the curve. If I take the entire area under the curve, that includes this area that I do want in the right-hand tail, but it also happens to include some area that I don't want in the left-hand tail. So I just have to take away the stuff that I don't want. So specifically, I want to take away the area that's to the left of 1.735. Or in other words, I can write probability Z bigger than 1.735 as 1. The total area under the curve is 1, because it's a probability distribution, minus probability Z less than 1.735. I like to think of this in terms of pictures. I think the pictures help you keep everything straight. But this is just the complementary event rule, right? From basic probability theory. I note over here that this area should be less than 50% and quite a good bit less than 50%. But now the probability that I have to look up is a left tail probability. So this is going to be a 1 minus, and then probability Z less than 1.735. That's about probability Z less than 1.74. So I'll come over to my table. I'm looking for an area to the left of a positive Z-score. The 100th place is 1.7. So unfortunately, because I'm on Chrome, I can't really select my row here, but you can see the 1.7 row that starts with 0.9554 and goes over. And I'm looking for probability Z less than about 1.74. So I'll go over to the column corresponding to 400ths or 0.04. And I see that the intersection of that row and column gives me 95.91%. So 1 minus 0.9591 is 0.0409 or 4.09%. That is less than 50%, and kind of as we would guess over here, it's quite a lot less than 50%, so that seems right. And just as a reminder, this was one approach, the complementary events approach, or the kind of building up the area that we want by starting with the area under the whole distribution and taking away what we don't want. So that's kind of the complementary events approach. We had a second approach. So we've completed the problem, we're done with the problem, but if we want to do it a separate way, we could have also done it this way. We could have said, okay, I'm looking for the area to the right of 1.735. And I could have leveraged the fact that the normal distribution is symmetric about its mean, about 0. And I could flip the whole thing about 0, right? The problem I have is I am asking for an area in the right tail, but my table gives me information about left tail. So how do I convert a right tail to a left tail? I could use a complement, or I could leverage the symmetry of the distribution. So when I flip the distribution about 0, the curve looks the same. 0 is, of course, in the same place, but my positive 1.735 flips over and becomes a negative 1.735. And my area to the right of 1.735, when we flip it over, becomes an area to the left of negative 1.735. So here we have probability z bigger than 1.735. And that's the probability z is less than negative 1.735. I can look that up on the table. If I go to my negative z-scores now, and I'm looking for an index of about negative 1.74. So the negative 1.7 row is the one that starts with 0.0446 and so on. It goes across. And then I'm looking for 400ths or 0.04. The column corresponding to 0.04 meets with the row corresponding to negative 1.7 and shows me an area or a probability of 0.0409. Exactly the same answer we got up here. So we could use symmetry, or we could use complementary events to answer this question. But we had to do something to convert the right tail area into a left tail area. And it's not a bad idea to just kind of have both of these tools in your toolbox, so you can use whichever one works best for that problem. We had also discussed a third type of probability we might be interested in finding, the probability that our random variable is between two numbers. So here I'm looking for this area. The probability z is between negative 0.35 and 1.24. And here I can't definitively say whether this is going to be bigger than 50% or less than 50%, because I don't shoot off out to positive or negative infinity in one of the directions. But just looking at it, it looks like it's going to be a substantial area, right? So I can maybe get a guess. It's not going to be like 5%, and it's not going to be like 95%. I could get an even better guess if I really wanted to push it and use like the 68, 95, 99.7 rule and chop this up into, segments to the left of -3, between -3 and -2, -2 to -1, and so on. I could look at each of those probabilities and get an even better estimate. But that's a heck of a lot of work. Maybe it's worth it in some cases, maybe it's not. But to set this up, here, symmetry doesn't really get us much, because if we flip over, we still have an area between two numbers. So here we'll use something more like the complementary events idea. So I need to turn this into a question about left tail areas. So I could construct the area that I want between negative 0.35 and positive 1.24. I could start by taking all of the area to the left of 1.24. And again, this includes the area that I want, that's between negative 0.35 and 1.24. But unfortunately, this includes a bunch of area that I don't want that's to the left of negative 0.35. So then I just subtract off the area that I don't want. So I subtract off the area to the left of negative 0.35. So what does this turn into? This is probability z less than 1.24. That's a left tail area, so that's good. That includes the area that I want, but also some extra that I don't want. So I just subtract off that extra probability z less than negative 0.35. And then we look up these two numbers on the table, we do our subtraction. And I'm not going to go through this work at this point, but this is the important part to understand. Are there any questions up to this point? Okay. So let's look at one more example from standard normal distributions. And that's here, probability z less than k equals 0.05. Or in other words, finding the 5th percentile of the distribution. So again, here I have a standard normal. I want to find a z index where the area to the left of that is 5%. In other words, I want to find a number k such that the probability z less than k is 0.05, or this area to the left of k is 0.05. I know the k is going to be a negative number, because if k was 0, the area to the left would be 50%. That would be too much area to the left. So it's got to be to the left of 0. And note that k is the z index that separates the bottom 5% of the distribution from the top 95%. That's just the 5th percentile. That's just another way of saying that it's the 5th percentile. So how do I approach a problem like this? Well, here what I want to find is I'm looking up an area, I'm looking up a probability, and I want to find the corresponding index. I know this is going to be a negative z-score result. Number one, because my picture looks more similar to the negative z-scores picture than the positive z-scores picture. And number two, because I know the index I'm looking for is negative. So I know I'm looking on this table, and I'm looking for an area to the left of 0.05. In other words, I'm looking in the field of the table. Let me see if I can bring up, let's see if Adobe is done with whatever shenanigans it was doing. There we go. Okay. So now I can actually select things again. Okay, so now I want to look in the field of the table in the middle here, where the areas, the probabilities are, and I'm looking for one that's close to 0.05. So I come down here, here's some 0.04s, and 0.05 turns out to be right in between these two, right in between 0.0495 and 0.0505, and that's one of these special cases. It's a special case that comes up quite often because a lot of times we're looking for a 5th percentile or 95th percentile. That's kind of a common thing that we'll be looking for in a bit here. And we note that the z-score, or the z-index, of negative 1.645 corresponds to an area of really close to 0.05. So k is about negative 1.645. Okay, any questions on standard normal distributions? Okay, give me 1 second. Be right back. Okay. So now let's move on to newer material. So now let's talk about general normal distributions. So here we have an example that we're going to use for the next several problems to work through. And that'll be taking a normal distribution where the mean is 100 and standard deviation is 15. So this might be like a model for IQ test results. The test results are actually, they call it norming the test results. They're fit to a normal distribution, often with this mean and standard deviation. Different IQ tests have different parameters they norm to, but quite a few of them norm to mean 100, standard deviation 15. So what does this distribution look like? I'm going to try to stick to a color scheme here. So I'm going to try to remember to keep my general normal distributions as black and my standard normal distributions as blue, just to keep things straight. So I'll try to roughly stick to that scheme throughout. So here I have X, a normal distribution, mean of 100, standard deviation of 15. So I'm symmetric about 100. These inflection points are 1 standard deviation away or 15 units away from 100, or they're located at positions 115 and 85. Now, something we might have remembered from a couple classes ago at this point was our normal distribution, our general normal distribution, the function that defines this curve had some constants and stuff, but it had an e to the minus x minus mu over sigma squared. And I suppose there's that 1/2 in front of here, but that's not the important part that I'm worried about. Specifically, this x minus mu over sigma bit. If I make a change of variables, z equals x minus mu over sigma, then this looks like some constant in front, again, e to the minus 1/2 z squared, or it looks like a standard normal. We might remember from chapter 3, this was called the z-score. So our z-score is the key to being able to translate any question in a general normal distribution, whether it's mean 100 standard deviation of 15 or mean 1,000 standard deviation of 500 or whatever it is, or mean negative 100 standard deviation of 4, whatever. We can translate any question about a general normal distribution into a question about a standard normal. And we know how to answer the questions about standard normals. We know how to answer questions about probabilities of left tail or right tail areas, or probabilities of the random variable being between two numbers. And we know how to answer inverse problems, finding z indices that are related to certain areas, whether left tail area, right tail area, maybe a symmetric middle area. We know how to do all of that already in standard normal. So that's going to be my strategy. I'm going to convert whatever question I'm asking about a general normal distribution into a question about a standard normal, answer it in standard normal world, so to speak, and then if needed, convert it back to the general normal distribution. Sometimes I'll need to do that last step and kind of convert back at the end, and sometimes I'll just get the answer in the standard normal world, and that's the answer. Okay, so let's look at these examples. So we'll start with probability x less than 100. And for some reason, I have like a green smudge on my screen. I don't know if that's coming up up on your side or not. I don't know if it's just like my computer was asleep over spring break or something and doesn't have enough coffee this morning or something or what, but seems like all of the tech is going a little crazy these days. Let me just try to erase it and see if, no, that doesn't do anything. Okay. So ignore the green smudge. I'm not sure why that's there, but probability x less than 100. If I look at my normal distribution, mean 100, standard deviation 15, and I'm looking for this probability x less than 100, I see that that's exactly half of the distribution. That's exactly the left half of the distribution by the symmetry of the distribution about the mean of 100. I know this has to be 50%. That's got to be the answer. Let's see if we can formally go through and get that answer carefully. So we start with a simpler problem that we know the answer to. See if we can derive that answer using this idea, using the idea that we want to convert the question in the X world to a question in the Z world. So kind of like up above where I converted the question still in the Z world, but the question about an area that wasn't really amenable to using the table, I converted that into a question or multiple questions where I could easily use the table. It's a similar strategy here. So when I go from the X world to the Z world, Z has mean of 0. I know I'm going to be looking for a left tail area, but what's the corresponding area in the Z world? Well, my relationship is Z equals X minus mu over sigma. Or in other words, my corresponding Z index, the Z index corresponding to the X index of 100 is X of 100 minus the mean is 100, over the standard deviation of 15. Or this is just 0. So Z equals 0 is the corresponding Z index in the Z world. And the area or the probability that I'm looking for is the left tail area to the left of Z equals 0. So I can say probability X less than 100, that's the same as probability Z less than 0. But now I can use my standard normal table, and I see probability Z less than 0.00 is exactly 50%. So this is the strategy that I'm going to use for really all of these problems, is reframe the question from the X world as a question in the Z world, get an answer in the Z world, and then if needed, translate back. Now here I don't need to translate back because a probability is a probability, an area is an area, so I just get the answer. If I was asking a question about an X index, I might get an answer about a Z index and then have to translate that to an X index. But for now, we won't have to do any translating back at the end. So what's probability X less than 115? Again, the same distribution that we're using all along here, mean 100, standard deviation 15. Well, a standard deviation of 15 means that going over to my inflection point, that spans 15 units. So this is 115 here. And again, I'm looking for an area to the left. So probability x less than 115 is this area here. I note that this is bigger than 50%. This includes all of the area to the left of 100, which is 50%, plus a bit extra. Now I want to reframe this question as a question in Z. I know my left tail area has got to be bigger than 50%, so my Z index has to be a positive number. But what positive number should it be? My corresponding Z index is going to be the X index I'm interested in, 115, minus the mean of the X distribution, 100, divided by its standard deviation, 15. Or this is 15 over 15, or 1. In other words, probability X less than 115 equals probability Z less than 1. And that's because 115 is one standard deviation above the mean of 100. But probability Z less than 1, I can look that up on my table. That's a positive Z score. I'm looking for a Z index of 1.00. The probability associated with that is 84.13%. That is bigger than 50% as I expected. So this checks out. Any questions so far? Okay, so let's look at another similar problem, probability X less than 123. I know my inflection point occurs at 115. 123 is a bit further to the right of that. So I'm looking for this area. I see this is going to be bigger than 50%. Again, because it includes all the area to the left of 100 plus some extra. If I want to think a little further, I can say, well, 115 would be one standard deviation above the mean, and 130 would be two standard deviations above the mean. I'm looking for an area to the left of something that's between 1 and 2 standard deviations above the mean. So that seems like it should be maybe in the 80 or 90% ballpark. Right. So a good bit above 50%, but I wouldn't expect to get a number like 98%. I'm going to reframe this in terms of Z. So this is X over here. And again, the X index I'm interested in is 123. What's the corresponding Z index? It's X minus the mean over the standard deviation of 15. Or this is 23 over 15. That is, and as an aside, I'm just writing equals now. I'm not being really careful about approximately equals versus exactly equals. Essentially, everything from this point on is going to be an approximation. So I'm not being super careful about writing approximately equals all the time. But we see that 23 over 15 gives me about 1.53. So the corresponding Z index to an X index of 123 is Z equals 1.53. And again, I'm looking for an area to the left. So 123 is just about 1.5 standard deviations above the mean, is what we're saying here. And we're reframing this as a more general question and asking, in a normal distribution, what's the probability of being to the left of a number that's 1.5 or so standard deviations above the mean? That answer is going to be the same no matter what normal distribution we're working with. We're generalizing away from, we're abstracting away from the specifics of this particular X distribution so that we can choose to answer in a distribution that's convenient for us, namely the Z distribution. So probability X less than 123, the number that I want, is the same as probability Z less than 1.53, which I can find. I go to my Z table. I know this is a positive Z score. 1.53 is a positive number. I'm going to look across the 1.5 row where that intersects with the 0.03 column. And I see I get 0.9370. Or about 93.7, 94%. This was maybe a little higher than I initially estimated. But if I do think back to my 68, 95, 99.7 rule, okay, this is kind of in the bounds that would be reasonable. It's definitely bigger than 50%, which was kind of my hard lower bound. And even if it's a little higher than maybe I initially suspected, maybe I was initially just ballparking it at like 80 or 90%. This is a little higher than that, but it's not like 99% where I'd be suspicious. So a little outside of my initial ballpark, but it meets my hard lower bound. And if I think back to my 68, 95, 99.7 rule, I say, okay, this does kind of make sense. So I'm comfortable with that answer. Any questions so far? All right, so let's look at a similar problem, but it's slightly different, right? There's a little hiccup here. Oh, probability X bigger than 110. So the main difference here is that I now have a right tail area. And I know that I'm going to eventually have to do two things. I'm going to have to turn my right tail area into a left tail area. And I'm going to have to turn my question about X into a question about Z, because I know how to answer left tail area questions in Z. Now I can ask myself, is there a better order to do the same? Should I switch the right tail area to a left tail area first, then convert to Z, or should I convert to Z first, then flip? Now, personally, I think it's always better to switch to Z as soon as possible. The reason is that in the Z distribution, you're dealing with numbers that are usually close to zero that are maybe a little easier to deal with. You have a nice symmetry about the zero axis, which means flipping over using symmetry is much easier. You just turn a positive number into a negative number. So my preference is always to switch to Z first. Now, I mean, if you chose to make it a left tail area first in terms of X and then switch to Z, that's not wrong. I think that just introduces some extra complexity. For instance, if you wanted to stick in X, but use symmetry here, you would have to flip about 100. So you'd be looking for a left tail area, but it wouldn't be like related to negative 110. It would be related to what? Well, 110 is 10 above 100, that acts as symmetry. So we'd have to be 10 below 100 or 90, right? Probability X less than 90. This seems to me to be pretty error prone. right? Because I'm flipping over an axis that's not zero. There's just a lot of places for me to make a mistake. I would prefer not to do this. Again, it's not that it's wrong. It's not that you're going to get the wrong answer. You get the right answer as long as you were super careful. But it's just that there are more places to make a mistake. So my preference is always to switch to Z first. I know that the X index I'm interested in is 110. So the corresponding Z index is 110 minus the mean over the standard deviation of 15. And again, we're just using this same normal distribution for all of these examples so you can track how these different changes, how these different changes in the question correspond to changes in the answer. That's why we're using the same normal distribution for all of these. It keeps one thing constant while changing other things. You know, this isn't like the only other normal distribution there is. I just want to be clear about that. But 110 minus 100 over 15, that's 10 over 15, 2/3, or that's positive 0.67 or so. And I'm looking for the area to the right of that. So probability X bigger than 110 is probability Z is bigger than 0.67. Now I have a question in Z, which is great, but it's a right tail area. And I have two ways to handle this. I can either use complementary events, make this 1 minus probability Z less than 0.67, or I can use symmetry. I'll choose to use symmetry here. So if I flip over, my curve looks the same when I flip about 0. My positive 0.67 flips over and becomes a negative 0.67, and my right tail area flips and becomes a left tail area. So it's probability Z less than negative 0.67. And when I look at negative Z scores, I know I need negative 0.6 for the 10th place. And then I need 0.07 for the 100th place. So coming down this column, in the negative 0.6 row, it looks like this gives me 0.2514. Or 25.14%. Does that check out with the size of this area over here? Yeah, it does. This has to be less than 50%. 25% is less than 50%, so checks out. So another similar problem, probability X bigger than 86. Again, same normal distribution we've been working with, mean of 100, standard deviation of 15. So 86 is to the left over here. And I'm looking for the area to the right of that. I know this is going to be bigger than 50% for my answer. This includes all the area to the right of 100 to the middle of the distribution plus some extra. Again, my preference is to switch to Z right away rather than trying to manipulate this into a left tail area in the X world where things are maybe a little more error prone. So I would immediately reframe this as a question in Z. The X index I'm interested in is 86. The corresponding Z index, 86 minus the mean of 100 over the standard deviation of 15. Or what does this give me? Negative 14/15. or about 0.93. So negative 0.93 is the corresponding z index that I'm interested in. Or in other words, from the perspective of x, 86 is about 0.93 standard deviations below the mean of 100. And the type of area I'm looking for is a right tail area. So probability x bigger than 86 equals probability z bigger than negative 0.93. Now I have a question in z, which is great, but I have a right tail area while my table gives me left tail area. So I need to convert that right tail area over to a left tail area. And here I'll use complementary events. Just because we did the last one with symmetry, we'll just show the different method here. I can construct the area that I'm interested in by starting with the whole area under Z. Again, this includes the area that I want, but also some that I don't want. Specifically, the area to the left of negative 0.93. I don't want that area, so I need to take it away. And these are all Z, of course. Or going from our pictures back up to probabilities, what is this? Probability Z bigger than 0.93 is 1, the total area under the distribution, minus probability Z less than negative 0.93. I can look up this probability directly on my table. That's a negative z-score, right? That's probability is corresponding to this picture. This looks like my negative z-scores picture. So I'm looking up negative 0.93. Here's my negative 0.9 row, and here's 0, 1, 2, 3 hundredths. So the probability that I'm looking to plug in here is 0.1762. And again, sometimes you can get caught up in a problem and you can maybe get your 0.1762 and think, great, I got the answer, and be ready to type it into my stat lab. Remember, I'm looking for an area that's bigger than 50%. 17% is not, so that check can help sometimes, especially when we're doing these kind of complementary events problems. It's sometimes really easy to forget to do that 1 minus at the end. If we're being super careful about everything, we won't forget it, but sometimes we get, a little excited, we get the answer off the table and want to just plug it in, but it doesn't mesh with our expectation of the answer being bigger than 50%. And we notice, okay, yeah, I have to subtract from 1 first. Whoops, have to subtract from 1 first. So 1 minus 0.1762 gives me 0.8238. That answer is bigger than 50%. So that passes the check. 82.38% is the answer for this problem. Okay, let's skip over this one just for time considerations, because this next one is essentially the same. Let's look at the probability that x is between 95 and 105. So the third type of problem that we had encountered. We've seen how to solve some left tail problems, some right tail problems. What about a problem that doesn't extend into either tail? Remember, x, as has been the case for the past several examples, we're dealing with x being a normal distribution, mean of 100, standard deviation of 15. I know that my inflection points are at 85 and 115. And I want to know the probability x is between 95 and 105. So 95 is just a bit to the left of 100, 105 just a bit to the right of 100. And again, I don't really have a great estimate for the size of this area, but I would know that 85 is one standard deviation to the left of 100, one standard deviation below the mean. 115 is one standard deviation above the mean. And the area that I'm interested in is certainly smaller than that area. That's smaller than the area that's within one standard deviation of the mean. So this should be less than 68%. Right? The area within one standard deviation of the mean would be 68%, again, from our empirical normal rule back in chapter 3. And we know this area is smaller than that. So this at least gives us some ballpark. And even though this interval of 10 units here is maybe seeming like a pretty small interval, we might be tempted to guess that it's a small probability, but it's also right in the middle of the distribution where the probabilities are the highest. So it's kind of two forces balancing out a fairly small interval, but it's in an area where there's like the meat of the distribution. If it was a small interval way off in one of the tails, we'd say, oh yeah, really small probability. But here we're not really so sure. But you know, the best we can easily say is less than 68% or so. Now, again, I could try to set up two left tail questions in X and then convert to Z. But my preference is always to convert to Z as quickly as possible. So this is 95 and this is 110. These are the two X indices that we're looking for, that we're interested in. I want to rephrase this as a question in Z. So I want to rephrase this as a question that looks like probability something less than Z less than something else. I need to figure out what these two numbers are. So now I have two X indices of interest. I need to figure out their two corresponding Z indices. 95 minus the mean of 100 over the standard deviation of 15. Well, that's negative 5 over 15, negative 1/3. That's negative 0.33. And the Z index corresponding to the X index of 110. Sorry, I copied that wrong. This should not be 110, it should be 105. I just copied this number down wrong for some reason. But the Z index corresponding to an X index of 105, 105 minus 100 over 15, or that's positive 5 over 15, or positive 0.33 for this index. And my 0.33 was running into my other zero in the middle there. But I now have a question in Z. I need to find the probability Z is between negative 0.33 and positive 0.33. And again, probably the easiest way to do that is to use the kind of the idea of complementary events. I start off with the whole distribution. Oh, not the whole distribution. Jumping the gun a little bit there. I start off with the whole distribution to the left of 0.33. That includes the area that I want. that is also to the right of negative 0.33. But it also includes a bunch of area in that left tail that I don't want. So I need to take away the area. That's to the left of negative 0.33. Or this is probability that z less than positive 0.33 minus probability z less than negative 0.33. So I have two z probabilities to look up. Let me erase these, just get a little extra space here. Probability z less than positive 0.33, that's on my positive z-score side. Here's my positive 0.3 row and my 300ths column. That gives me 0.6293. And then I need to subtract off probability z less than negative 0.33. So that's on my negative z-score side. And my z-index is negative 0.3012 So that's this 0.3707 that's in the 300ths column and the negative 0.3 row. So 0.3707. As an aside, we could have used some symmetry here to tackle this problem. The symmetry in our distribution matches the symmetry in this interval. So if you're interested in taking this a step further, you can look at how we could have used symmetry to only have to do one table lookup. But two table lookups is not a big deal. And now we can do 0.6293, 0.6293 minus 0.3707. And that gives me 0.2586 or 25.86%. This does mesh with our expectation that's less than 68%. And it's not some teeny tiny probability. Again, we did have an interval of size 10 in the meat of the distribution where there's a lot of probability accumulating. So this seems like a reasonable answer, about 25% chance that X falls between 95 and 105. Are there any questions on anything so far? So we've gone through a few examples of the three types of, you might call them forward problems in X, in general normal distributions, where we have a certain X interval and we're looking for the associated probability. What if we wanted to look at our inverse problems? What if we wanted to find, say, percentiles of this X distribution? So what if I wanted to find the 98th percentile of this distribution? So what's the question? I'm going to kind of write it a little bit smaller over here. So what's the question? I want to find the 98th percentile. I know that's going to be pretty far to the right to have 98% area to the left. I want to find the X index. I'm going to call it X subscript 98. It's an X index with area to the left of 98%. So I'm looking for an index given an area. This is an inverse problem. And it's quite often the case that with inverse problems, we kind of do the steps that we would have done for, say, a forward problem up here, where we're given an index looking for an area. And we kind of, in some abstract sense, do them backwards. And that's what we're going to see here. right? If I switch this into a question in Z, the Z index I'm looking for is what I would call P98, the 98th percentile of the standard normal distribution. So remember that notation P subscript 98 specifically refers to the standard normal. So I'm actually going to start in the standard normal, find the 98th percentile of the standard normal distribution using my table. That's the first thing that I'm going to do here. And then to get X98, I need to convert back. I need to use my Z-score, that the Z index of interest, P98, equals the X index of interest, X98, minus the mean over the standard deviation. But I really want to solve for this, right? Because I'll have looked this up off the table and know what it is. And of course, I'll be given mu and sigma as part of the problem statement. So if I'm going the other direction, if I know Z and want to find X, well, then I have X equals mu plus Z sigma. That's just solving our Z-score equation, Z equals X minus mu over sigma, just solving it for X. Okay, so let's go through and actually solve this problem. So here I'm going to start in the Z world. I'm looking for a Z index with 98% area to the left of it. I know this Z index is going to be to the right of 0 because the 0 Z index has 50% area to the left of it. I need more area than that. So this is going to be a positive Z index. So I'm going to look on my positive Z score side of the table. And I'm looking for area to the left of 98%. So in other words, when I look in my field here in this bunch of areas or probabilities, I'm looking for one that's quite close to 0.98. And I see some that are around here. I see 0.9798, 0.9803, 0.9798 is just a hair closer. So I go with that one. And this gives me a corresponding Z index of 2.05. And I don't know why it's selecting things crazy again, but 2.05 is my Z index. The Z index 2.05 is the 98th percentile of the Z distribution. It separates the bottom 98% of the distribution from the top 2%. But now I need to convert that back into the X world. So again, how am I going to convert back and forth between the Z world and the X world? Well, I have my Z score here that I've solved for X in terms of Z, or in terms of P98. Remember, the P98 is related to the standard normal. So I have that X98 is what? Mu, the mean of the X distribution, that's 100, plus P98, that was what I looked up, that's 2.05, times sigma, the standard deviation of the X distribution. times 15. Or this is 100 plus 2.05 times 15, or 130.75. So 130.75 is the X index that has 98% area to the left of it. Again, this is kind of an inverse question where we're starting with the knowledge of the probabilities or areas, and then trying to figure out what the indices are, or the index in this case. It's an inverse problem. It's kind of the opposite of the way we were looking at the problems before. So our procedure is kind of a little bit of the opposite. We start in the Z world, get an answer in the Z world, and then we have to translate that back to an answer in the X world. But 130.75 is our answer here. It's the 98th percentile of this distribution. What about the 25th percentile? Well, again, we'll use the similar strategy. We know this is an inverse problem, so we'll choose to start in the Z world. The 25th percentile, that's an area to the left of 25%. That's going to be to the left of 0 for that Z index. And I'm looking for P25, the 25th percentile of the Z distribution. So let me come over to my normal table. I know that this is going to be a negative Z index. So I'll go to my negative Z scores, and I know I'm looking for a left tail area of 25%. So I'll look in the middle of the table here in the field of the table for 0.25 or something close to that. And I see that it occurs right between these two, 0.2483 and 0.2514. 0.2514 is just a little closer to 0.2500, 14 10,000ths off, where 0.2483 is 17 10,000ths off. So I'll go with 0.2514. That's a little closer. And I see that corresponds to an X index of negative 0.6. And if I follow this column up, that's 7/100ths. So I see P25, the 25th percentile of the Z distribution, the standard normal distribution, is negative 0.67. Or in other words, the Z index of negative 0.67 separates the bottom 25% of the Z distribution from the top 75%. But now I need to translate this answer into an answer corresponding to the X distribution. So what is X25, the 25th percentile of the X distribution? Well, again, remember we have Z equals X minus mu over sigma. But if we solve that for X, we have X equals mu plus Z sigma. So if I know Z and I want to find the corresponding X, if I know the Z index, I want to find the corresponding X index, I just use the Z score formula, but this way. So X25 is mu, the mean of the X distribution, 100, plus P25, the 25th percentile of Z, or negative 0.67, times the standard deviation of the X distribution, 15. Or 100 minus 2/3 of 15 is 90. So this is 90. In other words, An IQ of 90 separates the bottom 25% from the top 75% of IQs, or it's at the 25th percentile. Any questions so far? All right, and then the last example that we'll do related to this specific normal distribution, the top 10% of IQs are at or above what number? So what are we looking at here? We'll draw just a little schematic up here. So here's X, 100. I'm looking for the top 10%, so I'm looking for the X index with 10% area to the right. I know that this corresponds to a question in Z with 10% area to the right. And again, there's two ways I could look at this. I could look at this using symmetry. I could find the 10th percentile of Z, which is going to be a negative number, and then just make that index positive. Or I could find the 90th percentile of Z and just stick with that answer. That's going to get me the same answer either way. I can use symmetry, find the 10th percentile of Z, the Z index with 10% area to the left. That's going to be a negative number, and then just flip it, flip the sign, make it a positive number to get an area to the right of 10%. Or I could use a complementary events type approach and say, well, 10% area to the right is the same as 90% area to the left. That's just the 90th percentile of Z. So whichever way you would like to do it, but we need to start in the Z world. Again, this is an inverse problem where we're given an area to start with, and we're looking to find an index. So we start in the Z world. We did have a notation for this. We called it Z sub 0.1. So the notation can get a little cumbersome when we're going back and forth between probabilities and so on, but we don't even need that notation here, that critical value notation. We can just call it something like K. So we're looking for a K such that probably Z bigger than K is 10%. And like I said, I think the easy way to do this is to use symmetry, mainly because that keeps our numbers the same. 10% stays at 10%. We don't have to flip from 10% to 90% or anything like that. So if I flip everything over this axis of symmetry 0, the curve looks the same. K becomes negative K, and the 10% area to the right becomes a 10% area to the left. So I find the 10th percentile of Z. That gives me negative the answer I'm looking for. And then I just get rid of the negative to make it the answer I'm looking for. So I'm looking for the 10th percentile. That's somewhere around here. There we go. 0.1003 is closer to 10% to 0.1000 than 0.0985 is. So I'll go with this one. My corresponding Z index is negative 1.28. So negative K equals negative 1.28, or K equals 1.28. The top 10% are 1.28 standard deviations above the mean, is how we could say it more generally. And now I want to switch this into the X distribution. And here I'm kind of thinking of the left picture being translated over. And again, remember I have z equals x minus mu over sigma. We should be comfortable with that equation now. And if we solve this for x, I multiply by sigma, I add mu. X equals mu plus z sigma, or x equals 100 is the mean. The z index that I found, that's the z index of interest, is 1.28 times the standard deviation of 15. So I need to go 1.28 standard deviations above 100. And that's 119.2. So I can say the top 10% of IQs are at or above 119.2, and that's my answer in X. Again, because I am given an area and I'm looking for an index, that's an inverse problem. I kind of start in the Z world, get the answer there, and then I have to translate it using my Z-score or a rewritten version of my Z-score, translated into the X world. Any questions on any of this? Okay, so let's look at an example then, because we've done a whole bunch of examples with the same normal distribution. Let's look at one with a different normal distribution, right? I wanted to keep the normal distribution the same as we went through all those examples so that there was kind of one constant, and we could see how the different examples are treated differently. But now what if we have a fresh problem? So suppose that masses of quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.06 grams. And suppose that we have a vending machine, and one of the tests that it does to try to verify that something that somebody puts in the machine is actually a piece of currency, and to be able to tell, quarters apart from dimes or whatever. The vending machine will reject quarters with masses outside of this range. So it balances, it gets the mass of the quarter and asks, is that between 5.64 and 5.70? If not, then it rejects the quarter. What we might be interested in is what proportion of real quarters will be rejected, right? If we reject too many real quarters, people can't use our machine very well, right? If you need to put in $1 worth of quarters, and if you need to have 10 quarters to get it to accept 4 of them, nobody's going to use that machine if it just keeps popping your quarters out one after the other. So let's try to figure out what proportion of true quarters will be rejected under this, under these settings, and then ask if we think that's reasonable. Do we think there's too many being rejected? Do we think it's, a reasonable number? So what do we have here? We have, let's call X the mass of a randomly chosen quarter, a randomly chosen real quarter from the population of real quarters that are out there. It's normally distributed with a mean of 5.67. Everything will just be in grams, so we won't carry that unit around, and a standard deviation of 0.06. And we kind of want to know what's the probability that 5.64 less than X less than 5.70. This would be the probability that a randomly chosen quarter is not rejected. We're asking for what's the proportion of quarters that will be rejected, or what's the probability that a quarter will be rejected. So we really kind of want to know 1 minus this probability. Okay, so let's just work on this probability, and then we'll try to remember at the end to do a 1 minus, right? Well, it's always a good idea when we get an answer to always just check back again with, okay, what exactly did the problem statement ask for? Am I answering it correctly, right? Before finalizing the answer. So if we just look at this probability, My X distribution has a mean of 5.67, standard deviation of 0.06. Oh, question in chat. Yeah, sure. Yeah, I can stick around for a couple minutes after class. I do have another class that's kind of right on the tails of this one, but I can chat for a minute or two. Or you can always feel free to shoot me an email. Just as an aside on emails, I'm still catching up with my spring break emails. I caught up on some of them this morning, but I'll catch up on the rest of them this afternoon or evening. So, uh, yeah, sure, yeah, definitely. Yeah, so you can shoot me an email. I should get to it later, either this afternoon or later this evening. Okay, but our standard deviation of 0.06, so we see the inflection points here at 5.73 and at 5.61. I'm looking for the area between 5.64 and 5.70. I'm looking for this area. I'm thinking this area is going to be kind of small. This region where I would, roughly speaking, accept a quarter. I mean, it might have to pass some other tests, but just from the perspective of this test, my acceptance region seems to be pretty small. It seems to be pretty unlikely that a real quarter will be accepted by my machine. So just glancing at this, I'm not super confident that this is a good setting for my machine, but let's go through the numbers and make sure that my suspicions are correct. So I'm going to write these down here, 5.64 and 5.70. Again, I could try to turn this into two left tail questions in the X world, but I don't like working too much in the X world. There's just a bunch of different numbers in every problem that we have to deal with. Let's switch into Z right away. So my two X indices of interest are 5.64 and 5.70. Let's find the corresponding Z indices. So one of them is Z is 5.70 minus the mean of X, 5.67, over its standard deviation, 0.06. Yeah, if anybody has questions on homework extensions or anything, just send me an email. And if you have sent me an email and I haven't gotten back to it, just you can send me a reminder if you want to, or this afternoon or evening, I should be caught up on all my emails. So yeah. So this is our corresponding Z to the X index of 5.7. And I see that this is 0.03 over 0.06. That is 1/2, 0.5. Be careful, this is a Z index of 0.5. This is not a probability. This is a location, 0.5. And then similarly, if we go through a similar calculation for 5.64, we're going to see Z equals negative 0.5. Nice symmetry here in this problem. So probability X is between 5.64 and 5.70. We could rephrase that as the probability that Z is between negative 0.5 and positive 0.5. And then we see that this can be made of the areas, or the area to the left of 0.5. That includes the area we want in the middle here. But it also includes this left tail area that we don't want. So we have to get rid of the left tail area. Scrunching in a little bit here on the right side, but I think we see where this is going. We've done this a few times already. This is probability z less than 0.5 minus probability z less than negative 0.5. Again, I always recommend, even when you get comfortable with these, that you write the pictures out, because it's just so easy to get one of these inequalities backwards or one of the signs, positive or negative, backwards or something. The pictures help so much. They don't take that much time to write out, especially if you do them not super carefully. They don't take much time to write out. But these are two questions I can look up off of my table, probability z less than 0.5. So I'm looking for 0.50 as my index, and I see that's 0.6915 for the probability. And then probability z less than negative 0.5. This is negative 0.5 row, and the 0/100th column is just that first column there. 0.3085 for that area. And then I take that difference, 0.6915 minus 0.3085. And that gives me 38.3%. Okay, what was my question? If the machine rejects quarters with masses outside of this range, what proportion will be rejected? Well, again, that was 1 minus the probability that the quarter's mass is within that range. So these are the ones that are kind of accepted, at least according to just this test. So rejected is going to be 1 minus. And then if I do second negative sign, it puts in this answer, this ANS descriptor. That's just referring to my previous answer. So 1 minus 0.383 is 0.617. So 61.7%. That's probably not acceptable, right? If I have a vending machine that rejects, say, nearly 2/3 of real quarters, it's going to make my machine very hard to use. I'm not going to get much business on that machine. So kind of a challenge question, and the answer to this question will come in the confidence interval chapter, but kind of a challenge question related to normal distributions. What if we wanted to accept the quote middle 95% of masses? In other words, we could, after doing this, we could reinterpret this setting of lower and upper bounds for the acceptable masses. We could see that corresponds to accepting the middle 38.3% of masses. Note that this interval is symmetric about the mean of 5.67. So this is the middle 38.3% of the distribution. I'm accepting the middle, in a sense, 38.3% of quarters, and rejecting anything that's further into either tail. What if I said, okay, I want to accept the middle 95% instead? So the 19 out of 20 real quarters will work in my machine. What should my revised lower and upper bounds be? It shouldn't be 5.64 to 5.7. Those are too tight. Those reject too many quarters. So what should my lower and upper bound for the mass that I'm willing to accept be, so that I accept the middle 95%, and I only reject a total of 5% of quarters? Or another way you could look at it by the symmetry is, can I find the 2.5 percentile and the 97.5 percentile and accept everything in the middle of that, so that only the lightest or least massive 2.5% of quarters and the heaviest or most massive 2.5% of quarters are rejected? So if you want a challenge problem, try to answer this. It's certainly doable. based on what we've done before, it's going to feel a little bit like, let me go back to the last lecture. It's going to feel a little bit like, it's going to feel like this problem, which I've scribbled all over, but so if you need a hint, look back at the lecture before spring break at this problem, and this will be a very helpful problem to help with this challenge question. Okay, so that wraps up the ideas of probabilities related to standard and general normal distributions. When we come back, we'll start talking about sampling distributions and the central limit theorem, and we'll start with an example and then move on from there. So that finishes up for today. I'll stop the recording.